So next up, we're going to introduce the arc length in polar coordinates formula. Now, from the stuff that we did with parametrics, the total arc length is going to be equal to the definite integral from t equals t1 to t equals t2 of the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. We're going to integrate that with respect to t. Now, in polar coordinates, if we're going to parameterize in terms of a variable, the variable that we're going to use is going to be theta. So keep in mind that if x is equal to r times the cosine of theta and y is equal to r times the sine of theta, in a previous video we differentiated both of these things with respect to theta. And these were formulas that I said absolutely do not memorize these. So unfortunately I need to re-get them. So first times derivative of the second, that's going to be negative r times the sine of theta plus dr d theta times the cosine of theta. dy d theta is going to be first times derivative of the second plus the second times the derivative of the first. So dr d theta times the sine of theta. Now, if we're going to try to set up this integral, that means that we're going to have to square both of these and add them together. So I'm going to take dx d theta, I'm going to square it, I'm going to add to it dy d theta squared. So we will be responsible for squaring negative r sine theta plus dr d theta times the cosine of theta. That'll be squared. And we're going to do the same thing for dy d theta. That'll be r cosine theta plus dr d theta times the sine of theta. And we're going to square that as well. This is why I always say that FOIL is my second favorite four-letter F word, because we are about to have a lot of fun. And the fun just has way too many letters. So, FOIL this guy, we are going to get r squared sine squared theta minus 2r dr d theta sine theta cosine theta. That comes from our inner and outer terms, plus dr d theta squared times the cosine squared of theta. That's just from expanding this set of parentheses. Now I'm going to expand this set of parentheses in a similar fashion. And this will be r squared times the cosine squared of theta plus 2r dr d theta sine theta cosine theta plus dr d theta quantity squared times the sine squared of theta. Now, if that just doesn't look like the most fun formula that we derived today, I just don't even know what's going on. There is some great news as far as this is concerned, though. And the great news is, if you take a look at this term right here and this term right here, they happen to be the exact same term, one with a minus and one with a plus, which means that they will cancel each other out. There are two terms that both contain an r squared, so what I'm going to do is put those together and factor out the r squared. If I put them together and factor out the r squared, then I am going to get sine squared theta plus cosine squared theta. You'll also notice that there are two terms left that both contain a dr over d theta quantity squared, and if I factor that out, I will get sine squared theta plus cosine squared theta from this term and this term. Good news is the Pythagorean identity exists, which means that those sine squared theta plus cosine squared thetas will become 1s, giving us the following quaint little formula: r squared plus dr d theta quantity squared. That lets us know that the arc length formula in polar coordinates is going to be the definite integral from alpha to beta of the square root of r squared plus dr d theta quantity squared d theta. In my next video, we'll actually do a couple examples where we use this formula.